Welcome to the deep dive. Our mission today is a really highly targeted intervention. It's designed for one specific purpose, to inoculate you against the most common, well, the most tricky architectural misconceptions and questions on the AZ-104 Azure Administrator exam.
Right.
This isn't about reviewing what a virtual machine is. It's about understanding the specific patterns Azure uses to exploit common administrative assumptions.
That's precisely the goal. We've basically distilled a comprehensive guide that analyzes all these failure points across every major domain: identity, networking, governance, you name it.
Storage, compute, hybrid.
Yeah, all of them. These are the spots where, the documentation might be a little ambiguous or where two services interact in a way you just wouldn't expect. And that's what leads to failure.
We're looking for those shortcuts to proficiency. So our focus isn't just learning the facts, but really internalizing the why behind the architecture, especially when you have multiple Azure services that have to cooperate. We've got 35 specific cross-cutting traps identified, and we are going to unpack every single one.
And if you can master these traps, you really move beyond just knowing the Azure commands. You start to understand the nuances, the hierarchy, the policy enforcement order, and how identity control planes differ from data access planes. That's the level of understanding you need to pass.
Okay, let's jump right into identity and access, because this feels like where a lot of administrators stumble right out of the gate. It's a foundational concept that Azure splits control into two entirely separate realms, which brings us right to trap one, confusing the management plane and the data plane.
This is arguably the single most critical distinction you need to internalize for any Azure certification, really. You will, without a doubt, see a scenario where a user is assigned the powerful contributor role on a resource, let's say a storage account.
Right.
But then the user reports they can't read, they can't write, they can't even list the actual blobs inside the containers.
And the natural reaction is just confusion. Contributor sounds like it gives you, carte blanche. If I can manage the resource, why on earth can't I manage its contents?
Because contributor is strictly a management plane role, you have to think of the management plane as everything you do to the resource through the Azure Resource Manager, through ARM.
Okay, so creating the storage account, deleting it, maybe adjusting its network firewalls, changing its redundancy settings.
Exactly. All of that is the management plane.
So if we use an analogy like a high-security warehouse, the contributor role lets me own the warehouse. I can hire the security guards, I can change the locks on the main door, I can even tear the whole building down.
Perfect analogy, but it does not give you the key to the specific boxes or pallets stored inside that warehouse. To interact with the content, the blobs, the files, the queues, you have to operate on the data plane.
So what's the implication for the exam? What's the correct fix when a contributor can't read the data?
The fix is to assign a specific data plane role. For storage accounts, this means roles like storage blob data contributor or storage blob data reader. These roles, they completely bypass ARM and they authorize direct interaction with the data service endpoint itself.
So you have to look for those trigger words, something like user can manage, but not read-write blobs.
That's the tell. If it's managing the resource, think contributor or owner. If it's touching the content, you have to think data plane roles.
That clarity helps immensely. And it builds on that because Trap 2 highlights the confusion between the two entirely separate role systems that exist in the Microsoft ecosystem.
Yeah, this is the confusion between Microsoft Entra ID roles and Azure Resource Roles, or RBAC. The classic scenario is a really powerful user, a global administrator, who just cannot, for the life of them, access or manage a virtual machine.
And the administrator's first thought is, well, if I'm global admin, I should be able to do anything in the subscription.
And that assumption is just a fundamental misunderstanding of the boundary. Global admin is the highest authority, yes, but within the Entra ID tenant structure, it controls identity, users, licenses, groups.
Services like Exchange Online, things like that.
Right. But crucially, Entra ID roles grant no implicit permissions to resources living in the Azure Resource Manager. No VMs, no VNets, no storage accounts, nothing.
So the global admin title is purely for identity management, not infrastructure management. How do they get access to that VM then?
They need an Azure resource role, something like owner, contributor, or reader assigned specifically within the Azure subscription structure. The exam is testing whether you understand that these two systems are almost entirely independent when it comes to resource access. You need the right key for the right lock.
Okay, so once we know we need an Azure resource role, we hit another trap. This is trap 4, overlooking scope and violating least privilege. The exam loves to give you a situation where multiple scopes, like the resource itself, the resource group, or the whole subscription, could technically work.
And the principle of least privilege, which you have to adhere to for the exam, it dictates that you limit the scope to the lowest possible level necessary.
So if a user only needs to manage a single VM, giving them contributor on the entire subscription is wrong.
It's defined as a failure of administrative best practice. It creates this huge, unnecessary blast radius. If that user account gets compromised, the attacker now has control over every single resource in the subscription, not just that one VM.
That makes sense.
So if the requirement is managing a single VM, assign the role at the resource level. If it's managing all components for one application, the VMs, the database, the network, then you assign it at the resource group level.
And you only go to the subscription or management group level if the role truly needs that broad access.
Exactly. Always start small.
Our final identity trap for this section, trap 3, deals with tenant boundaries. And this is the assumption that managed identities work across tenants.
Managed identities, or MIs, are phenomenal. They let resources authenticate to Azure services securely without you having to manage credentials, but they rely on the resource being registered in the local Entra ID tenant.
Which means they are tied directly to the resource identity within that specific directory.
And because of that, MIs are strictly tenant-bound.
So if my VM in tenant A needs to pull a secret from a key vault in tenant B, which is a totally legitimate cross-organization use case, the managed identity just fails. Why is it architecturally restricted like that?
Well, the restriction is really rooted in security and federation boundaries. MIs are seamless because they implicitly trust the local tenant. They just aren't designed for the complex trust negotiation you'd need for cross-directory access.
So what's the administrative solution when the scenario says you have to do cross-tenant communication?
You have to use the tool designed for federation, which is a service principal. This means creating an application registration in tenant A, granting it rights in tenant B, and then using the client ID and secret or a certificate for authentication.
So if you see cross-tenant or multi-organization on the exam.
Rule out managed identities immediately. Look for the service principal option.
Okay, moving into governance. This is where concepts of enforcement and hierarchy really start to confuse people. There's this tendency to think one tool does everything, which leads to misapplication. This brings us right to trap 5. Locks do not secure configurations.
This is a classic misdirection in the scenario questions. The requirement will be very specific, something like, the company mandate is that all new storage accounts must have geo-redundant storage enabled, or ensure all VMs are tagged with a cost center.
And the proposed solution and the multiple choice options will be something like apply an Azure read-only lock to the resource group.
Right. And a read-only lock, it sounds so powerful, it implies preventing unauthorized changes.
But it doesn't prevent misconfiguration, does it?
It does not. Locks are purely for preventing administrative actions on the resource scope itself. So, resource deletion, renaming, modifying top-level properties, they're guardrails against accidents or malicious resource destruction.
So the lock stops me from deleting the VM, but it doesn't look inside the VM's configuration to make sure it's compliant with our standards.
Exactly. To enforce configuration standards, you have to use Azure Policy. Policy is the mechanism designed to inspect the JSON resource configuration before deployment using a deny effect, or to audit it after deployment with audit or deploy if not exists.
So policies for tags, specific SKUs, disk types, regional restrictions.
All of that. Never choose a lock when the scenario is about configuration enforcement.
That sets us up for the ultimate hierarchy check, trap 6. Policy deny overrides RBAC, even owner. This is a crucial concept for understanding Azure's security model.
Yeah, a lot of people coming from traditional on-prem systems, they assume that the person with the highest access rights, the owner, can always override system limits. So the exam will present a scenario where an owner tries to create a resource, let's say a storage account, and the action fails.
And the immediate assumption is that the owner role must be missing some permission.
But the correct answer hinges on the evaluation order inside the Azure Resource Manager.
And what is that order?
The evaluation order is sacrosanct. Governance is checked first. If a policy deny assignment has been applied, it doesn't matter what role the user has, the request is blocked. RBAC is only evaluated after policy has confirmed the resource request is compliant with the organization's rules.
Can you walk us through the architectural choice there? I mean, why does Azure prioritize policy over owner rights?
It's a design principle rooted in central control and compliance. Governance has to be able to set hard, non-negotiable boundaries for the entire organization. boundaries that no single administrator, not even an owner, can accidentally or intentionally bypass.
So if an owner could bypass a policy deny, the whole governance system would be unreliable for compliance mandates like ISO or HIAPIA.
Precisely. The solution to the failure is always fixing the policy or granting a specific policy exemption, not messing with the RBAC rule.
Okay, moving on to standardization. We hit Trap 7, which deals with blueprint deprecation. If the exam offers blueprints as a primary solution for standardization, we need to flag that as outdated.
Right. Blueprints used to be Azure's all-in-one solution for defining a reusable package of standards resource templates, RBAC assignments, policies, all bundled together to apply to new subscriptions.
The concept is sound.
The concept is sound, but the service itself is now deprecated.
So if the learner needs to enforce a complete standardization baseline across new subscriptions today, what is the current recommended toolset?
The modern approach is much more modular. It uses a combination of tools you already have. You use management groups to define the hierarchy and scope. You use policy initiatives to bundle your related policies, and you use template specs to standardize your repeatable ARM templates.
So that modularity has replaced the single blueprints service.
All right.
Finally, in governance, we have Trap 8, which focuses on the hidden ripple effects of organizational changes. Moving a subscription changes inherited policies.
This is a great diagnostic trap. A scenario describes a subscription where deployments worked fine for months. Then, the subscription gets moved from Parent Management Group A to Parent Management Group B, and suddenly, all deployments fail with access errors.
And the administrator, they look at the user's RBAC roles and find nothing has changed.
And they're totally stumped.
So why does the failure happen?
The moment the subscription changes its parent management group, it inherits a completely different set of policy assignments. Management Group B might have a policy initiative assigned that Management Group A did not, and that policy might include a deny effect that is now blocking the deployment.
So the failure is often misinterpreted as an RBAC issue because the end result is just access denied, but the root cause is the change in the inherited policy.
Always check the policy assignments if there have been structural changes.
Okay, Azure networking. It's notorious for its nuances, and here, mixing up security controls is a critical failure point. Let's start with Trap 9. Service endpoints are not private network access. This distinction between service endpoints and private endpoints is absolutely foundational.
It really is. It separates the administrators who understand the security implications from those who only know basic connectivity. Let's define them again clearly because the security guarantees are totally different.
Okay, start with service endpoints.
A service endpoint does two main things. One, it routes traffic destined for Azure PaaS services like storage or Key Vault over the secure, optimized Microsoft backbone network. It avoids the public internet.
Okay.
And two, it injects the identity of your VNet or your subnet into the request, which allows the destination service to recognize the source. But, and this is the crucial part, the destination resource still presents a public IP address.
So it's optimized and secure within Microsoft's infrastructure, but the service is still technically accessible via its public interface, assuming the resource firewall allows it.
Exactly. Now, a private endpoint is fundamentally different. It maps that destination service to a private IP address within your virtual network. This connection completely removes the service's public endpoint from your network path. It provides true network isolation.
And that distinction explains the exam trigger. If the scenario explicitly calls for strict isolation, eliminate public exposure, or restrict access only to this VNet, the only correct answer is a private endpoint.
Absolutely. Service endpoints will fail that requirement for true isolation. The language is key. Service endpoints are about performance and backbone routing. Private endpoints are about absolute network security and isolation.
Next, we hit a hidden dependency in Trap 10 related to load balancer health probes.
A very common scenario. An administrator sets up an application gateway or an Azure load balancer, configures the backend pool with VMs, but the VMs are always marked as unhealthy. Traffic isn't being routed. They check the application and it's running just fine.
So where is the failure hiding?
The failure is almost always the network security group, NSG, on the backend VMs or the subnet. The health probes that originate from the Azure LB infrastructure have to be explicitly allowed access. If the NSG is too restrictive, it blocks that probe traffic.
What's the specific configuration detail needed to allow those probes in?
The NSG needs an inbound rule that uses the Azure Load Balancer service tag as the source, and it needs to target the specific port the health probe is listening on, usually 80 or 443. If that specific service tag isn't allowed, the probe fails, the VM is reported as unhealthy, and the load balancer just stops sending traffic to it.
Let's tackle the most fundamental routing trap. Trap 11 VNet peering is not transitive.
This one trips up everyone coming from a traditional networking background. If you have a hub and spoke topology, so VNet A is a spoke, VNet B is the hub, and VNet C is another spoke, and you peer A to B and B to C.
Right.
A resource in VNet A cannot communicate with a resource in VNet C by default.
But why does Azure make peering non-transitive?
Peering is designed to treat the two connected VNets as a single, flat, non-routed segment. It's like a simple Layer 2 style bridge. It doesn't automatically update the routing tables of VNet A to know about the address space of VNet C, even though B knows about both of them. The hub is just a passive connection point, not an intelligent Layer 3 router.
So to fix this and enable A to talk to C via B, we need to introduce some intelligence.
Exactly. The solution requires adding an active network component to VNet B, the hub, that can perform routing. This usually means an Azure firewall or a network virtual appliance, NVA, or in bigger enterprise settings, a virtual WAN. These services actively manage user-defined routes and forwarding, and that forces the traffic through the hub appliance and solves the transitivity problem.
Okay, sticking with peering, Trap 13 is the hardest blocker. Overlapping address spaces prevent peering.
This is a scenario where the fix is painful, but the architectural restriction is absolute. If VNet A uses the IP range 10.1.0.016 and VNet B also uses 10.1.0.016, you cannot, under any circumstances, establish VNet peering between them.
And the exam loves the trick of suggesting, oh, just configure a UDR to solve the routing conflict.
That is the wrong response. Routing tables, UDRs, they're irrelevant here. Azure needs unique address spaces to know which VNet the traffic is supposed to go to. If they overlap, the routing is ambiguous from the start, and the peering operation just fails to even initialize.
So the only solution is to change the CIDR block of one of the VNets.
Which often means a full migration or rebuild of resources in that VNet. It's a big deal.
This leads perfectly to Trap 14. UDR overrides system routes. What happens when we implement the common security practice of forced tunneling?
Right. So forced tunneling is when you create a user-defined route, a UDR, for the default route that's destination 0.0.000, and you point it to a firewall or an on-premise gateway. This forces all outbound internet-bound traffic through a single controlled point for inspection.
The trap here is that this UDR overrides all of Azure's system routes.
It does.
And what critical internal traffic suddenly breaks.
Crucially, traffic to internal Azure services that are technically accessed via a public route but use Azure's internal metadata services. Things like licensing checks, monitoring endpoints, or the VM agent talking to the Azure platform, all of that will break.
Because the system routes that normally manage this internal platform communication get overridden.
And the traffic is instead routed out the tunnel and gets lost. So to implement forced tunneling safely, the administrator has to add exceptions. You have to add specific UDRs or network rules that allow the required Azure service tags to communicate directly with the Azure platform, bypassing that 0.0.0000 forced tunnel.
Okay, circling back to private endpoints, we revisit the logical component that often breaks the physical connection. This is Trap 12. Private endpoints require private DNS integration.
You can configure everything perfectly: the VNet, the subnet, the private endpoint, the target service firewall, and yet access fails. The administrator sees the private endpoint has a private IP, say 10.1.1.5, but when they try to access the storage account by its name, storageaccount.blob.core.windows.net,
the client device doesn't know to look for 10.1.1.5.
it doesn't. It's resolving to the public IP address, which is probably firewalled off.
Because the missing piece is the private DNS zone.
Exactly. Azure needs that specific DNS zone, privatelink.blob.core.windows.net, to map the service name to the private IP. And this zone must be explicitly linked to the VNet where the client device is. Without that link, the client uses its default DNS, which is often public, resolves the public IP, and the connection fails. This is a crucial trap. Networking relies entirely on correct name resolution.
Let's shift our focus to storage and compute. Performance and security policies often overlap in complex ways here. Starting with security, we look at Trap 15. Standalone SAS tokens are not revocable.
Right. Shared access signatures, or SAS tokens, are powerful temporary keys you can generate that grant really granular access to storage containers or blobs. The critical security knowledge here is that once a standard SAS token is created using the storage account key, Azure has no way to monitor or invalidate that specific token. It's a bearer token for its entire lifespan.
That sounds like a huge security headache if a standalone token with a long expiry gets leaked. How does the administrator regain control or revoke access instantly?
They only have two options. The most drastic one is to regenerate the storage account keys that were used to sign the token. This instantly invalidates all SAS tokens generated using those keys.
But that's a huge disruption.
It's a massive disruption. The smarter, more granular option, and the one to look for on the exam, is to use a stored access policy at the container level.
And how does that policy help with revocation?
Well, a stored access policy defines the permissions and the expiry time centrally on the container. The SAS token you generate then just references this policy, rather than being signed directly by the raw storage key. Since the policy itself is an Azure resource, an administrator can just modify or delete the policy, and that instantly revokes all SAS tokens linked to it without disrupting the entire storage account.
We should also just reinforce the identity trap from Section 1, specifically applied here. Trap 16. Blob access requires data plane roles. Just to hammer it home, if you have contributor on the storage account resource, you still need storage blob data reader or contributor to touch the data inside.
That's right. That separation of management and data planes applies universally. It is a recurring pattern that the exam tests relentlessly across all pay-paste services, not just storage.
Okay, so let's look at a complex interaction between networking and storage in Trap 17. Disabling public access on storage break service endpoints, unless whitelisted.
This tests whether the administrator understands that network restrictions apply even to what they think of as internal Azure traffic. So an administrator implements a service endpoint on their VNet, believing this allows internal access over the Azure backbone. Then, separately for security, they go to the storage account firewall and disable public access entirely.
And they expect success when they try to access the storage account from the VNet with the service endpoint, but they just hit a wall. Why?
Even though the service endpoint routes the traffic via the Azure backbone, the storage account firewall still sees this as incoming network traffic. If public access is disabled, it acts as a total block. To connect successfully, the administrator must specifically whitelist the source VNet subnet within the storage account's network firewall settings.
So the firewall needs explicit confirmation that the subnet linked by the service endpoint is allowed, even if the main public setting is off.
Correct.
Moving to Trap 18, Azure Files AD authentication nuances. We need to differentiate Azure Files from blob storage when it comes to enterprise identity.
Azure Files provides cloud-based SMB file shares, which requires traditional file system semantics, NTFS permissions, access control lists. The exam tests the knowledge that Azure Files supports 3 distinct authentication methods: native Microsoft Entra ID authentication, integration with on-premises Active Directory domain services via domain controllers, and also Azure ADDS.
But what's the core differentiator here that links back to our earlier traps?
The key is realizing that only Azure Files supports these hierarchical SMB and NTFS permission semantics that you need for corporate file sharing. Blob storage is object storage. It does not support SMB or NTFS protocols or permission structures. If the scenario involves legacy applications that need domain-joined file access, Azure Files is the answer.
Okay, finally for storage. Trap 19 is a terminology trap. Versioning exists, but is not the same as backup.
Yeah, Azure Storage has excellent native data protection tools. Soft delete protects against accidental deletion for a set retention period, and blob versioning automatically retains previous versions of a blob whenever it's modified.
An administrator might rely solely on versioning, thinking it fulfills the organizational backup requirement. Why is that potentially not enough?
Well, versioning and soft delete are highly granular object-level recovery tools. They're excellent for self-service or minor rollbacks. But the term storage backup typically refers to a comprehensive disaster recovery solution provided by the Azure Backup Service, which is a completely separate offering.
And backup provides application consistency, full file share recovery points, long-term retention policies.
Right. It's often used for Azure File shares, and it fulfills enterprise-level DR demands that simple versioning just does not meet.
Now, focusing on compute and availability, we have Trap 20. Availability sets are not availability zones. It's all about scope.
This is a test of blast radius understanding. If the scenario demands protection against a zone-level outage, so the failure of an entire data center due to a major event like a flood, a fire, or a sustained power loss, the only correct architecture is availability zones.
And what specific type of failure does the older concept availability sets address?
Availability sets protect against local hardware failure within a single data center or zone. They make sure your VMs are distributed across different server racks, which are fault domains, and are updated sequentially in update domains. They protect you from a single rack power supply failure or a physical server crash. crash.
If the whole building goes offline.
The availability set fails completely. The exam distinguishes between internal resilience, which is sets, and regional resilience, which is zones.
Trap 21 deals with performance upgrades, VM resizing limitations. What are the silent killers that prevent a VM resize from working, even if the desired size is available in the region?
The most common failures are rooted in the physical constraints of the underlying hardware cluster that's hosting the VM. The two main culprits are, first, trying to resize the VM across different VM families. For example, moving from a standard D series to a memory-optimized E series.
That seems logical. Different families require different underlying hardware. What's the second more opaque constraint?
The second is the limitation of the current hardware cluster. The cluster the VM is physically deployed on might not have the capacity or the necessary hardware extensions to support the new size you want, even if it's in the same VM family.
So if that hardware cluster can't support the new size, what administrative action is necessary to proceed?
You have to stop and deallocate the VM first. Deallocating forces Azure to release the VM from its current physical cluster. When you then attempt the resize or a restart, Azure is free to provision the VM onto a different, compatible hardware cluster that has the necessary resources available.
Finally, Trap 22 Link's business needs infrastructure choices. Azure disk types matter.
You have to be able to translate those vague performance requirements into specific SKU choices. If the scenario mentions a need for high IOPS, low latency for transactional workloads, or guaranteed provision performance, you have to select premium SSDs or, for mission-critical, high-throughput needs, ultra disks.
And conversely, if the focus is on cost management for non-critical assets.
If the requirement states low cost, infrequent access, or development test environments, then the choice should be the corresponding cost-optimized tier. That's typically standard HDD or standard SSD. These decisions are almost always tested as trade-offs between performance and expense.
Okay, moving into observability, let's focus on how data is collected and routed. Trap 23 is a simple administrative error, but it's a fundamental architectural truth. Diagnostic settings must be explicitly configured.
This is often overlooked because administrators assume that since Azure Monitor is a core service, all the logs just flow to it automatically. This is incorrect. Azure Monitor collects basic platform metrics automatically, but the detailed operational logs,
Like specific resource activity logs, security audit logs, or deep VM diagnostics.
right, none of that is collected unless the administrator takes an active configuration step.
So if the administrator needs to troubleshoot a resource using specific operational logs, and they can't find the data in log analytics, what is the prerequisite step that was almost certainly missed?
They must have missed configuring the diagnostic settings for that specific resource. This setting is what tells Azure, please export the specific category of logs and send them to this designated sink, which could be log analytics, storage, or an event hub. If that setting isn't explicitly configured, those rich logs simply don't exist anywhere to be queried.
This feeds right into Trap 24. Logs versus metrics confusion. They serve fundamentally different purposes, and that leads to using the wrong tool for the job.
Metrics are numeric data points. They're collected frequently, and they're highly optimized for speed and alerting. They tell you what is happening right now. CPU utilization is at 90%, or the queue depth is increasing. They are perfect for real-time alerting and dashboards.
And logs.
Logs are structured data records. They're designed for historical analysis, for auditing, and for complex pattern matching. They tell you why something happened, user X logged in from IPY, or this resource failed deployment because of that specific policy. Logs require you to use the Kusto query language, KQL, for any effective investigation.
So if the scenario involves analysis over a long period, like 30 days, or searching for specific events, you need logs. If it involves immediate response and threshold alerts, you need metrics. That distinction helps in deciding the tool. Now, let's discuss Trap 25. Matching monitoring data landing zones to requirements. Diagnostic data can be sent to 3 primary destinations, and you have to select the right one based on the end goal.
The exam tests if you know the purpose of each sync. So if the requirement is integration with a SIEM system like Azure Sentinel or some third-party tool, the data has to be sent to an event hub. Event hubs are designed to stream huge volumes of data instantly to external consumers.
What if the requirement is long-term compliance or archival, outside of the normal log analytics retention period?
That requires sending the data to storage, specifically blob storage. It's the most cost-effective solution for long-term retention, sometimes for 7 years or more, as mandated by compliance standards.
And finally,
Finally, if the primary goal is operational visibility, rich analytics, and KQL querying by the operations team, then the data has to go to a log analytics workspace.
Okay, transitioning to hybrid connectivity, we start with trap 26. Azure DNS does not resolve on-prem queries automatically.
When an administrator establishes a VPN gateway or an express route circuit, they've successfully created the physical or logical data tunnel between Azure and their on-premises network. But that tunnel is just the pipe. It doesn't magically extend the naming service.
So if a VM in Azure needs to find a server named DCEST01 in the on-premises network, it has no inherent way to do that just because the connection exists.
That's right. Azure DNS cannot natively resolve those on-premises private names. The necessary step is logical configuration. The solution requires either setting up conditional forwarders in Azure to point specific domain queries, like corp.local, back toward the on-premises DNS servers over the tunnel, or deploying the new, more robust Azure DNS Resolver service to handle that redirection and linking.
Trap 27 is an architectural dependency for ExpressRoute. ExpressRoute requires a virtual network gateway.
Administrators sometimes visualize the ExpressRoute circuit connecting directly into the VNet itself. Except in the very specialized and rare ExpressRoute Direct scenarios, this is incorrect for standard deployments.
What's the purpose of the gateway in the ExpressRoute configuration?
The virtual network gateway acts as the required termination point and translator. The ExpressRoute circuit terminates at the provider's edge and connects into Microsoft's network, but that connection has to be integrated into the VNet's routing infrastructure via the gateway. The gateway handles the routing and ensures the VNet's resources can use the ExpressRoute private peering path.
So always include the gateway in your ExpressRoute design.
Always.
And finally, for hybrid, Trap 28 deals with VPN gateway ski limits. Performance and capability are often silently constrained by the initial choice of tier.
The ski isn't just about price, it's about hard limits. If the scenario describes low throughput or connection instabilities when transferring large amounts of data, the current SecU is likely insufficient and needs to be scaled up. For example, from basic to VPN GW1 or higher.
And for advanced routing capabilities, what's the crucial SKU limitation?
If the requirement includes using BGP, the Border Gateway Protocol, for dynamic routing table updates between Azure and the on-premise network, the basic VPN SKU is explicitly restricted. It cannot support BGP. You have to select standard or higher tiers for BGP functionality.
We have reached the culmination of our deep dive. This section focuses on the traps that require synthesizing knowledge from two or more domains: identity, network, governance, storage. And these are usually the trickiest, highest scoring questions on the exam.
These are the scenarios where one system works perfectly, but the failure of an adjacent, seemingly unrelated system causes the whole process to fail. You really have to troubleshoot layer by layer here.
Let's start with a complex network interaction in Trap 29. Private endpoint breaks VNet peering connectivity expectations. This combines the private endpoint security model with the non-transitive nature of peering.
Okay, so imagine VNet A, where the user sits, is peered to VNet B, which is the hub. A private endpoint for a highly secure key vault is created inside VNet B. A user in VNet A tries to access the key vault, and the connection fails.
And the administrator says, but we have VNet peering, and we already solved the transitivity issue with an NVA in VNet B. Why can't VNet A reach the key vault's private IP in VNet B?
The routing might be correct if an NVA is involved, but the fundamental failure is almost always DNS resolution. The key vault's private IP only exists in the context of the private DNS zone that's linked to VNet B. When the client in VNet A tries to resolve the key vault's name, it can't access the private DNS zone linked in VNet B.
So it defaults to the public resolution, which is blocked by the key vault firewall.
Exactly. The solution isn't just routing, it's explicitly linking the DNS. For private endpoints to work across VNet peering boundaries, you have to ensure VNet A can resolve the private IP. This usually means linking the relevant private DNS zone to VNet A as well, or setting up DNS forwarding so VNet A knows to ask VNet B's resolvers for the private IP.
The exam tests, if you remember, that PE access is useless without correct DNS linking.
Precisely.
This sets the stage for the ultimate validation scenario. Trap 30, the identity plus private endpoint interaction checklist. When access fails via PE, you have to check 3 independent layers.
The trap is set when the learner confirms layer 1 is correct. They say the user has the necessary data plane RBAC role assigned to the target service, like Key Vault Reader, but the failure persists and the learner assumes the role must be wrong.
So if identity is confirmed correct, the remaining failure has to be network or service security. What are the 2 remaining checks?
Layer 2 is private DNS. Check if the service name resolves to the correct private IP address. That means validating the private DNS zone linkage to the source VNet. If that link is missing, access fails. Layer 3 is the target service firewall. Even if the DNS resolution works, the key vault or storage accounts firewall might be explicitly blocking the source subnet. You have to ensure the source VNet or subnet is explicitly whitelisted in the target service's networking settings.
The question really tests the maturity of the administrator. They have to be methodical. Identity is correct. Move to DNS, DNS is correct. Move to the firewall.
Exactly. A failure at any one of those three independent layers results in a total access failure.
Let's look at a security trap that dictates where control is enforced. Trap 33. In NSG, applied to a private endpoint, NIC does nothing.
This is a subtle but really important piece of architectural knowledge. When you create a private endpoint, a network interface card, an NIC, is provisioned in your VNet with the private IP. An administrator, wanting to microsegment, might try to apply an NSG directly to this PE NIC to control traffic.
And the attempt to apply control at the NIC level just fails. Why is that?
The private endpoint represents a specialized, highly optimized, non-routable link to the Azure backbone. Traffic control is architecturally enforced at the destination service. The NSG on the PE NIC is just bypassed because Azure requires you to use the specific security controls built into the target PARAS service.
So the correct administrative action to control who accesses the key vault via the private endpoint is where?
The control has to be applied at the key vault firewall settings or the storage account firewall settings. At the source of the resource, you specify which VNets or subnets are permitted to connect. Using an NSG on the PE NIC is an ineffective red herring.
Now back to governance. Trap 31. Forcing private endpoints via policy. Deploy if node exists. How do we ensure resources are deployed securely without just denying every deployment that isn't perfectly configured?
Well, a simple deny policy that says you can't create a resource if its public endpoint is enabled is administratively clumsy. It blocks development and it requires manual remediation. The advanced preferred governance solution is the Deploy If Node Exists policy effect, or DINE.
And DINE provides the sophistication needed here.
It does. DINE policies audit the creation request. If an administrator tries to deploy a storage account without configuring a private endpoint, the DINE policy won't deny the deployment. Instead, it triggers a remediation task. This task automatically executes a linked ARM template to create the necessary private DNS zone and the private endpoint resource, bringing the deployment into compliance after the fact.
So it enforces the standard without halting necessary operational work.
Correct.
Moving to another structural dependency, Trap 32. Subnet delegation confusion. This often causes PES employments to fail silently.
Certain foundational PSS services, particularly those that need to inject their own network components into your VNet like Azure SQL Managed Instance or Azure Container Instances, they need specialized control over the subnet. They can't operate if the subnet is just treated as a standard VNet segment.
What configuration is required on the subnet to allow this specialized control?
The subnet has to be delegated to that specific service. Delegation is a commitment that allows the Azure service to inject specific service endpoints, security policies, and network configuration hooks into that subnet. If a deployment of one of these PACE services fails with an obscure networking or permission error, checking that the host subnet is correctly delegated is often the solution.
Okay, Trap 34 forces us to decide between the two major network filtration tools, Azure Firewall versus NSG tasks. The decision rests entirely on the layer of inspection required.
The distinction is really about depth and scope. NSGs operate primarily at layer 4, so TCP/UDP ports and IP addresses. They are decentralized, cheap, and they're used for microsegmentation for controlling basic traffic flows within a VNet.
What does Azure Firewall add that NSGs cannot handle?
Azure Firewall is a centralized security appliance that operates from L3 all the way through L7. Its key advantage, and the exam trigger, is its ability to perform FQDN filtering. That's filtering traffic based on fully qualified domain names, like www.contoso.com, and NSG cannot read the domain name inside the HTTP request.
So if the scenario requires restricting outbound internet access to specific domain names, the only correct tool is the Azure Firewall.
The only correct tool.
Our final combo trap, Trap 35, is the practical but often forgotten financial consideration, cost misconceptions for storage and network egress.
The exam tests basic optimization principles. If your compute resources, like a VNet with virtual machines, are accessing storage accounts located in a different Azure region, the traffic crossing that geographical boundary is considered egress traffic.
And what is the consequence of that cross-regional egress?
It results in significant data transfer charges. Egress charges are often the highest network cost component in Azure. The principle being tested here is architectural efficiency. The recommended practice to minimize cost and also reduce latency is always to co-locate compute and storage resources within the same Azure region, and ideally within the same availability zone.
So if the scenario involves high data transfer rates between services in different regions, the problem is inefficient architecture leading to high cost.
Absolutely.
We've covered a massive amount of detail, moving from basic identity separation all the way through to these complex multi-service dependencies. Understanding these 35 cross-cutting traps gives you the necessary insight to not just answer a question, but to actually troubleshoot the real scenario.
We can really synthesize all this knowledge into three fundamental meta patterns that you see throughout the AZ-104 exam design.
Okay, first, always differentiate between the management plane and the data plane. If the requirement is configuring the resource itself, creating, deleting, setting properties, it's the management plane. Use contributor or owner. If the requirement is manipulating the content inside that resource, reading or writing blobs, fetching secrets from a key vault, it's the data plane. Use the storage data roles or key vault secrets user roles. That split is constant.
Second, you have to remember the ultimate hierarchy of enforcement. Policy deny assignments are enforced first, and they take precedence over all identity roles, including owner. If a deployment fails and RBAC looks correct, the failure is a governance issue. The solution is in policy modification or exemption, never increasing a user's resource role.
And third, acknowledge the critical and often hidden dependencies in networking. Connectivity solutions like private endpoints and VNet peering are frequently broken not by a physical connection issue, but by a failure in the logical services they rely on. Specifically, incorrect DNS resolution or missing private zone linking that prevents that name-to-IP mapping.
These three rules transition you from just a fast memorizer to a truly competent Azure administrator who can diagnose failure modes at the architectural level. And that leads to a final provocative thought for you to consider as you study. When you analyze any security failure or access request in Azure, the first thing you must determine is not who is the user or which region is the resource in, but which specific operational plane management or data is the user trying to act upon. That fundamental distinction is the key to mastering the complex cross-service traps required for certification.